what needs to happen in the next couple of years for you to feel confident that you're on track with this, the grand plan that you have for your tech?
We have a current demonstration plant in Brooklyn, just in our backyard at the Brooklyn Navy Yard. And this one's doing tons of CO2 removal, capture, and storage per year. We test a number of different CO2 inputs. Sometimes we're working with CO2 in the natural waters, again, for that carbon removal process where we're reducing the outgassing. Sometimes we're injecting CO2 for that carbon capture. And over the next 6-9 months, we're continuing to do that testing with customer-specific inputs. We're working with customers across the different sectors that we've talked about: oil and gas, aluminum, cement, steel. All of those different process emissions have different characteristics. And so now we're testing those specific inputs at that current Brooklyn pilot over the next several months. And that's a huge unlock in being able to go to those customers we're working with and say, hey, this isn't something that we've done on paper or assessed on paper that it could work. We actually have data where we've used these same inputs that you have on your facility. This is the exact efficiency of the process. This is the cost of that process with your specific inputs. And the next step then is getting this technology on their site.
Well, welcome back to the Decarb Connect podcast. It's been a minute. It's been a minute since our last episode, and I feel like we are coming back strong with a really interesting discussion about a novel technology currently being put through the works in New York. And we're going to be talking with Garrett Boudinot, who is the founder and CEO of VyCarb. So Garrett, welcome. Thank you for helping me kick off this next phase of our podcast. It's good to have you here.
Thanks for having me.
So we will do the normal question that my usual listeners know about how you arrived at this point in time, but just as a bit of scene setting, VyCarb does fit into the part of our ecosystem known as CDR, but in a really novel way, removing CO2 from water and allowing water then to do some more of the heavy lifting, I guess, is a very, very simplistic way of describing what you do. But Garrett, why don't you kick us off with just a little bit more on what VyCarb is and does, but also how did you come to this point? How did you find yourself working in this space?
Sure. So in short, VyCarb is a carbon dioxide removal, capture, and storage technology company. As you said, we're based in Brooklyn, New York, and we've been around for about 2.5 years. And I think you hit the nail on the head. Our approach to capturing and storing CO2 uses natural water, and really mimics, accelerates, and controls the ocean and natural waters' existing pathway to capture and store CO2. And how I got here, it's really a direct extension from my upbringing and former life as a climate scientist. So I spent most of my career studying from an academic perspective how the ocean naturally is absorbing CO2, storing it for long time scales, how the carbon cycle in the ocean and atmosphere are evolving from climate change, and how that's impacting ecosystems and the oceans and abroad. That's very depressing work. And so having done that for several years, tracing those carbon cycle changes, those impacts, developing new analytical tools to be able to trace where the carbon, that invisible greenhouse gas, is going between the atmosphere and the ocean, I started to think about ways that we could, again, accelerate and leverage that for not just studying the problem, but actually implementing solutions. Fortunately, about the same time I was having that existential crisis and wanting to focus on solutions, there emerged stronger market interest in decarbonization, in capturing and storing and removing CO2. And so actually, initially I was led to start up a research program at Cornell University. Again, still in the academic realm, but focused on solutions, thinking about how we can accelerate some of these natural pathways. And then as I was doing that, I really saw a huge problem in at the time, several years ago, emerging nascent evolution of climate solutions, which was, again, how do we trace Okay, so we can store CO2, we can capture CO2. How do we actually trace it? How do we verify that that carbon was indeed captured and stored? And so, having developed several analytical chemistry tools to trace it, I said, okay, I've got a new idea now for how we can both leverage and accelerate the Earth and ocean's natural carbon storage pathways, but also develop a way to measure that so we can control it, so that we can verify it. And all of that is what led to VyCarb several years ago. I received what's called an Activate Fellowship, which is a really cool program in the US that provides funding and support for scientists like myself to develop out and commercialize new technologies that have high impact. They have a specific focus on carbon management that they started in 2022. And that was really what catalyzed VyCarb as a company. So very early on, we had an idea for a new sensing technology where we could trace the different kinds of carbon in water. So of course, we all know about CO2. That's what's in the atmosphere. The way the ocean naturally stores that carbon is by converting it to HCO3 and CO3, which are bicarbonate and carbonate. So CO2, HCO3, CO3, they're all present in all waters at all times, but the relative proportion varies depending on how much carbon is there in different chemical properties of the water. And so, just based on the elements that are in the ocean serves as a sink for carbon from the atmosphere by absorbing that CO2 and converting it to bicarbonate. So we developed a sensing technology that allows us to measure all three of those different compounds in water in real time. That was a real breakthrough. Mm-hmm. Traditionally, what we were doing as scientists for the past century is taking samples from the ocean or from waters, bringing it into a laboratory, running very expensive, labor and time-consuming analytical procedures. The sensor that we developed allowed us to, again, quantify these in real time. And once we had that, we were then able to design a full stack chemical processing system that combines CO2 with natural waters and then is able to accelerate and convert that CO2 into bicarbonate so that we can actually store CO2 from a range of sources permanently and safely. And because that sensor is integrated into the process, we can control the flow rates, control this whole chemical reaction to ensure that we're taking all that CO2 that we're adding, converting it all to bicarbonate, and that the chemical properties of the water, once it's converted to bicarbonate, ensure that it is stable, ensure that it is safe for release in those natural waters. And then the final thing I'll say is over those past 2.5 years, we've built out the team to do this. So VyCarb is a largely technical team of about 10 people based in New York. My background as a scientist was very helpful in developing the initial concept of the technology, but then had to rely heavily on engineers to actually bring that into reality and scale that up. So we've got a great team of engineers in ocean engineering, mechanical engineering, mechatronics, and then a number of other scientists on the team, all working on this integration of that sensing technology with that core chemical processing system to actually go from an idea to what is now a pilot demonstration in Brooklyn to where we're going, which is integrating this in industrial facilities all around the world.
So, I mean, there's so much in that journey, and I can only imagine like how your climate scientist brain has had to adapt to working with engineers, working with investors, working with industry, working through projects, where as a business, just in a bit of context, but a brief kind of bit of context, where are you at right now? So you've got this pilot. Where are you at in terms of funding or partnerships and things like that? And then we'll talk a little more about how you're engaging within industrials in particular.
Yeah, for sure. And you're absolutely right. It has been a learning experience and a journey for sure. I mentioned the Activate Fellowship. Early on, we received several non-dilutive funding opportunities. In the States several years ago, there was lots of funding going into development of new technologies for decarbonization, and we were able to take advantage of those everywhere from New York State, philanthropic, even at the federal government level through the Department of Energy. That provided some of the initial uh, resources to do the initial demonstration. Once we were able to show in real waters that we were able to capture and store CO2 permanently and fully measure that reaction, that was a real breakthrough. That was something that hadn't been shown before. And so then we started to get some good commercial traction in the voluntary carbon removal market. So we sold carbon credits to a number of the early carbon credit purchasers who were focused on, I think carbon credits historically have focused on things like, tree planting, reforestation, things like that. There was a new area of carbon credits several years ago that came up focused on engineered solutions and permanent solutions. So ways that we can more quickly remove and store CO2, ways that we can better verify that. And so those were some of the customers that we sold to initially. And once we had those sales, we were able to get proper venture capital investment. So we raised our pre-seed, our seed, and that was from a mix of certainly, institutional VCs in Silicon Valley and New York City and things like that, but then also a good amount of venture capital interest internationally. So we have investors in Norway, in Australia, recognizing the global interest in decarbonization. And then also, even at an early stage, one of the things I was really proud of is getting investment from some big strategic corporate partners as well. So groups like Rio Tinto and BlueScope Steel, who have active decarbonization efforts, who recognized a need in that decarbonization value chain and the solution that VyCarb is able to offer to reduce costs and accelerate the deployment of that decarbonization on their facilities specifically. And we'll be able to announce in the next month or so some of the new investors that we've been able to bring on as well, who similarly are major strategics that not only can be customers, can actually adopt this technology, but also help us scale it up.
And are those when you think about those industrial clients, especially Rio Tinto, BlueScope, and similar, for them is this kind of about solving? We often hear at Decarb about voluntary carbon credits being the last 5% or the last 10% of a given strategy. Is that the primary driver, would you say, for them engaging right now, or is it the investment opportunity? Like what do you see as being the real hook when you're having those conversations?
Yeah. I'll say for all of our investors, it's certainly both. There's the strategic opportunity and the financial opportunity here. All the CVCs, the corporate venture capital firms that we work with, still have a financial mandate. But what's really, I think, exciting for our investors about our technology is I'll say, differentiated technology portfolio that we have, but then also the differentiated opportunities that technology can tap into. So certainly voluntary carbon markets is where we've gotten our revenue thus far, is a big opportunity for us, but is also, any market in which the defining characteristic is voluntary is subject to fluctuations as corporate mandates and strategies change. And so one of the interesting and I think differentiated opportunities from our approach is that, yes, we can use this for the voluntary carbon markets where we're capturing naturally abundant CO2 and storing that. We would call that removal, carbon dioxide removal. But then the technology also works under what would be called proper carbon capture and storage, where we're taking, whether it's from fossil sources, from process emissions, CO2 that is actually being emitted at a point source, and storing that as well. Because really, yes, we're able to capture the CO2, but the value of our technology is that we're permanently storing it, and we can show exactly the final product, how much of that carbon is being stored. And in this value chain for so many of our customers and investors, it's probably an exaggeration to say 1 million, probably an exaggeration to say 1,000, not an exaggeration to say hundreds of different ways to capture CO2. There's lots of existing and emerging solutions there. There are very limited options for permanently storing that CO2. And so that's really where, yes, that has applications in voluntary carbon markets. It also has applications in direct decarbonization. And exactly to your point, companies might take 5 to 10% of their hard to abate emissions and offset those. That leaves 95% that they have to decarbonize on site. Some of that can come from electrification, but many processes will continue to emit CO2. So carbon capture and storage is critical there. And it's also worth noting that there are a number of different policy, we'll call them carrots out there, right? So tax incentive, things like in the US, 45Q has gotten a lot of attention. We've gotten confirmation through the Department of Energy that our approach also works for that. And so I think that means whether it's meeting, climate or decarbonization mandates, or meeting voluntary commitments, or being able to take advantage of new incentives, which is a revenue generating. Those are all the different things that VyCarb's technology can unlock for, again, these investors from a financial perspective or customers from actual adoption.
So that kind of definitely answers part of what would have been the next question, which is about, there are all these technologies out there. And at the same time, I would say, it's June 2025 at the point of recording this. The last month has not been pretty for a lot of CDR companies. So I guess you've probably already pulled in the answer here, but when you're, again, talking to those industrials, what is it that's making them say yes to this rather than to something else? Something that may in theory be further along, but, what's the yes coming from then? Is it, so we've sort of unpicked a little bit that it's, yes, there are those voluntary carbon market benefits, but is it really this permanent sequestration, or like where's the yes coming from in industry?
Yeah. I'll put it in the context of the incumbent solution. I think you alluded to this, right? There are very de-risked and at scale approaches for permanently storing CO2, and we can call that geologic storage. So in the US, we refer to Class 6 well injection as kind of the incumbent solution where you take CO2 and in specific geologies are able to re-inject that back into the ground, and it stays there. Has to be monitored over years or decades to ensure that it doesn't come back out. But the infrastructure's there. Oil and gas has been doing this for decades already for a number of different reasons. And so that is the kind of benchmark that folks compare VyCarb's technology to. And for a lot of our customers, they are looking at that storage solution and recognizing it's not really a solution for them for a few reasons. One, the geologic injection or sequestration is geographically limited. So if you're emitting CO2 and you're not already by a Class 6 well, you've got to get the CO2 to that geology, which requires pipeline infrastructure, which is a whole can of worms around permitting. But it also requires, both from the pipeline infrastructure and injection, that the CO2 is at incredibly high purity. So over 95% purity is what that CO2 has to be able to be transported and injected. That's a huge barrier because a lot of CO2 emissions are 1%, 5%, 30%. So you've got to then use a lot of energy to concentrate and compress and condense that CO2 to high purities. That's where quote unquote carbon capture comes in, or even carbon removal, things like direct air capture. Technologies that are able to take CO2 from a gas, where that CO2 is a very low concentration in that gas, and concentrate it up to over 95%. One of the really exciting things about VyCarb's solution is we can take very low purity CO2. So we're testing as low as 1% CO2 in gas form and able to permanently store that directly. So that's one reason. The other is because we're using natural waters, and this can be ocean water on coastline or offshore, but it can also be rivers or lakes, any large enough body of natural water. That means that the geographic limitation of storage goes away. So you don't have to build the pipeline infrastructure. If it's a CO2 emitting facility near natural water, all of a sudden you have access to that. Another reason that I think a lot of folks are interested in this is the volumes here. So in order to justify the capital expenditure for pipeline infrastructure and doing a geologic storage facility or project, the numbers only work out if you're emitting millions and millions of tons of CO2. And there are many facilities across industries: steel, cement, aluminum, oil and gas. The list goes on, where it might be emitting 100,000 tons, 500,000 tons, a million tons, 2 million tons. And at those climatologically significant volumes of CO2, it's not enough to justify all of the necessary infrastructure and expense for that incumbent solution. And that really leads us to the final reason, which is cost. So because we're able to do a full stack carbon capture and storage on site where there's water, you don't need the energy to compress and concentrate CO2. You don't need the pipeline infrastructure. You need access to water and some simple inputs for our process, which means that it's a much lower cost solution. We actually project that at scale, this can get well under $100 a ton, close to $50 a ton for the full stack solution. And I think ultimately, I just gave a long answer. It all comes down to that final one. It's a much cheaper solution at scale than what folks are looking at currently.
Yeah, that's hugely competitive. The things we hear most about in our membership are two things that you've just addressed. Obviously, cost, but it is to do like the main barrier to so many people doing post-combustion carbon capture is really to do with this concentration of their flue gas, or the nature of the gas that they have will mean that it's either not commercially viable or not technically viable, depending on what's going into that stack as well. So that's interesting. Okay, well, let's walk through the kind of the kind of chemistry of the bicarbonate conversion piece, and if you could sort of just talk about that a little bit more, and then explain, like, if you're a cement manufacturer or if you're a chemical company or an aluminium plant, like what does this look like for you? What's the footprint that you're going to have in addition to your site to get the kit in to make this work? But so let's tie the kind of what it is, just a little bit on the what it is into literally how does this look and feel on a site?
Absolutely. So on the chemistry side, I'll situate this in kind of how the ocean already does this. So CO2 in the atmosphere combines with water, rains down as carbonic acid in rainwater, and weathers rocks. So rains down on rocks on land that have elements like calcium and magnesium. And as that then is transported from rainwater into something like a river, the dissolved calcium and magnesium that has been dissolved from the carbonic acid, the magnesium and calcium are positively charged ions, and they buffer the carbonic acid into bicarbonate. And so it's CO2 plus H2O plus Ca yields Ca in dissolved form, calcium, plus bicarbonate. And so the bicarbonate is negatively charged, the magnesium or calcium is positively charged. And in chemical oceanography, we refer to these ions as conservative. And so anywhere that calcium or magnesium ion goes, the bicarbonate ion is going to stay with it to continue that buffering. And that's what leads to the permanence of this. So the residence time of these conservative ions like magnesium, calcium, and bicarbonate in the ocean is on the order of 100,000 years. So the ocean holds these for about 100,000 years before then it might be precipitated out as a calcium carbonate mineral on the seafloor. So that's long been understood in climate science as the long-term, we're talking millions, billions of years reaction that occurs when there's more CO2 in the atmosphere to then bring CO2 levels down. And it's what has driven the magnesium, calcium, sodium, and carbon chemistry of the oceans today. It's really, in chemical oceanography, we think of the ocean as just a big carbon chemical reactor, really, but between the atmosphere, those rocks, and then depositing in the ocean. Our system it's a modular system that is a continuous flow water reactor where we're adding in CO2, we're adding in natural waters that forms the carbonic acid, just like what happens in rainwater. And then to drive this pH mediated reaction, we're adding additional sources of calcium or magnesium. And we source those from often natural minerals, just like what happens in the Earth system, but these are natural minerals that are currently being mined for agricultural or aggregate or industrial processes. An easy example of one of the main inputs we use is calcium carbonate, limestone. So it's CaCO3. And so we're able to add, the CaCO3 goes into our reactor. That calcium is then dissolved by the CO2 and the carbonic acid, and we end up with two bicarbonates. One comes from the CO2, one comes from the CO3 of the mineral input. And so then that leads exactly to your next question around implementation. The reactor, the actual system itself is a pretty small footprint. We have to get the CO2 from the point of either emissions or, whether it's captured direct from flue gas, or, we work with direct air capture companies and things like that. So wherever the CO2 is, that has to be, there's a simple conduit to then bring that into our reactor. And so the main operational component here for our customers is then bringing on that mineral source of calcium and magnesium. And then it really becomes a sector specific question. So I mentioned cement. We work a lot with cement companies because they're already moving vast quantities of calcium carbonate, of limestone. And so they already have the supply chain necessary for our process. In addition to that, some of the outcomes, some of the byproducts of the cement manufacturing process generates high calcium and magnesium, I'll call them minerals, materials that are a waste. They don't go into the cement, and so they have to be disposed of. We've actually shown we can use some of those as well. So we can even use kind of a circular economy case. For other industries, things like the steel blast furnace process already also has a calcium carbonate input. So that makes a lot of sense. I'll contrast that with things like aluminum or oil and gas, where we would then, with those customers, we identify a source of suitable materials. And one of the things that's unique about VyCarb's process and how we're able to accelerate this reaction and control the reaction is we're able to use a number of different sources of calcium and magnesium. So to date, we've tested 12 different materials. Again, some of them are natural, some of them are industrial byproducts. And that flexibility on that mineral input is really what's a big unlock for scaling this. So, if we're at an aluminum facility that doesn't already bring in calcium carbonate, we're typically able to find several viable options. And so then we can select the one that has the lowest cost, the lowest transport distance, the lowest input emissions, because all of those are then calculated as part of that total life cycle assessment for the process. And so it's really a pretty simple, 3 inputs. If a facility has CO2 and is near water, it's an ideal candidate for our solution. And then we either, are able to increase the existing supply chain or bring in a new supply of that calcium or magnesium bearing mineral. And that's the final component to make this all work.
So as you're talking and thinking about literally the flow of water through this cycle, one of the things that comes up quite a lot and increasingly, I would say, in the last year is about wastewater on industrial plants. And I'm just wondering, is there any link? Is there any combination of that you can use in that, again, using that circular economy vibe, or is it an entirely different part of the process and not related?
Yeah, I mean, I love that question because that's a big part of the scale potential here. Our beachhead, really what we're focused on now are those emitting facilities or CO2 facilities that are already co-located with natural waters, just because that it's low-hanging fruit. One of the things we are exploring more, working with some different partners on, is being able to leverage wastewater. There is a volumetric ratio between the amount of water we use and the amount of CO2 that we're able to capture. And so that's really the key determinant here, is if there is sufficient industrial wastewater, and depending on where it goes, if it's being discharged into some reservoir that either ultimately ends up in the ocean or isn't transformed significantly through wastewater treatment, then that is certainly a viable option.
That sort of brings us then anyway to our next phase. So we've talked about, you've proven the tech in terms of how it relates to the voluntary market. You are starting to work with industrial partners. What is scaling up your supply chain, your technology require? What needs to happen in the next couple of years for you to feel confident that you're on track with this, the grand plan that you have for your tech?
Yeah. So I alluded to this earlier that we have a current demonstration plant in Brooklyn, just in our backyard at the Brooklyn Navy Yard. This is our third pilot, so we've been iteratively scaling up at different locations. And this one's doing tons of CO2 removal, capture, and storage per year. We test a number of different CO2 inputs. Sometimes we're working with CO2 in the natural waters, again, for that carbon removal process where we're reducing the outgassing. Sometimes we're injecting CO2 for that carbon capture or just carbon storage application. And over the next 6-9 months, we're continuing to do that testing with customer specific inputs. And so, we're working with customers across the different sectors that we've talked about: oil and gas, aluminum, cement, steel. All of those different process emissions have different characteristics, different purities or concentrations of CO2, different available inputs of calcium and magnesium there, different flow rates that we can achieve with those CO2 emissions. And so now we're testing those specific inputs at that current Brooklyn pilot over the next several months. And that's a huge unlock in being able to go to those customers we're working with and say, hey, this isn't something that we've done on paper or assessed on paper that it could work. We actually have data where we've used these same inputs that you have on your facility. This is the exact efficiency of the process. This is the cost of that process with your specific inputs. And the next step then is getting this technology on their sites. And I'll say, we're not going to go from tons per year to 1 million tons per year. And so there's an iterative scale up. And so a lot of the partners we're working with, continuing to bring in, are partners who are interested in really standing up some of these first of a kind projects. So these are often customers who either already have carbon capture on site and urgently need a storage solution, or are investing heavily in their overall need for decarbonization, and piloting is a big part of that. And once it's we call that a commercial pilot. So actually deploying this on an industrial facility, maybe not at 1 million tons per year, but several thousand tons per year. The next big de-risk that we have to show and that we're working with now is that ecosystem safety, that water quality safety component. So the output of our system goes right back out into natural waters. Our measurement integration allows us to control the process to ensure that the water is safe. But this is a first of a kind thing. Environmental regulation and permitting is something we take seriously. I have a background in climate science and environmental science. We want to get that right. And so doing that iterative scale up, starting with our current pilot and then an industrial integration, will allow us to continue to work with partners we already have, independent parties who are doing that ecosystem assessment to support scaling up further. I think that really answers your larger question here. Like, what's the unlock to get this globally? And it's showing it once at relevant scale, showing that it's effective at capturing and storing CO2, and showing that it's safe. I think once we've done those successfully, this is going to be a solution a lot of folks will really want.
Okay. So just to kind of link something you just said with your point about geologic storage, obviously that geological storage has a whole, the permitting landscape around that is incredibly complicated. Clearly, you must have some permitting issues to kind of navigate. So what's the if you imagine a typical industrial plant, if there is such a thing, what might be the kind of key permitting steps that would be needed? And is there a timeline? Is it relatively easy? What's your sense of that process?
I will speak in generalizations because it is a highly geographically and jurisdictionally variable answer. But generally, we talked about industrial wastewater earlier. A lot of the facilities that we're working with now already have wastewater discharge regulatory permits and limits to what the different elemental compositions of that discharged water is. And so there's strong precedence in any jurisdiction that we're working in for what's the total pH change that we can have on the output water, total calcium magnesium bicarbonate concentration of that output water. And so sometimes it is really straightforward. We're working with one partner who has one customer who has a existing wastewater discharge permit. We have very clear numbers. We are below all of those numbers. It's pretty straightforward. We just increase the volume that they need there. For our current system in Brooklyn, that was first of its kind and just operated by us. So we did need to get regulatory permission for that. And it was relatively straightforward, largely because we have that measurement integration within our system. So we're able to show real-time data of exactly what the chemistry of the water is as it's leaving. And we work with a number of independent third parties, whether they be academic research labs or private research institutions and groups who are also doing their own independent studies of what we're doing. So we're able to say, hey, you don't have to believe what our sensors and our data are showing. Here's work from a university, from a private research group, their independent studies that have shown that indeed, the concentrations of elements in the water, the chemistry of the water is indeed safe. And we're actually kind of throwing the kitchen sink at our current pilot with even doing a very in-depth ecosystem and basin-wide study of what are the impacts on things like dissolved oxygen and chlorophyll, some of these key ecosystem indicators to show there's no change. Actually, in some of the waters we work in, like the East River, they're already suffering from acidification. And that acidification is due to CO2 in the water. And so this process is actually our current pilot in some ways can be seen as a deacidification project that is just financed by, carbon incentives. And so that's also been really helpful.
I think that's interesting because I imagine there will be, the next wave of business development, client development that you do. Permit as a word can be a bit of a trigger word for companies that have been through the loop on a number of other projects. But the point is, it's a totally different kind of process. And yeah, that sounds really interesting. The idea of having the sensors and the data so embedded in what you're offering, I imagine goes a long way to kind of solving how people feel about new technology and so forth.
Absolutely.
So you've talked about the next 18 months in terms of the engineering side and what you need to prove and test. What about funding, the kind of partnerships you may need to develop this? What's kind of on the horizon for you?
Yeah, we've actually recently secured some partnerships. Some of those are with kind of equipment manufacturers that generate key components of the overall process for integrating this, where it's not our IP, but our IP, but we can work with folks who are already developing some of these or commercializing some of these core components. Things like how do you just move CO2 around in an industrial facility. So we're working closely with some of those folks, and I'd say a big focus for us right now is working with EPCs, so engineering, procurement, and construction firms. Each of our customers had, they work with EPCs for their own kind of as they develop projects. And so now that we've de-risked this technology and are continuing to at our current pilot, that then gives us also sufficient performance metrics and input data to now be working with a number of EPCs to then actually be able to have much stronger answers on exactly what this looks like for, again, a cement facility versus an oil and gas facility. So that's a big one. We were fortunate to receive some support from the U.S. Department of Energy to facilitate some of that work. So that's been great and has kind of catalyzed a lot of that work. And then the final one I'll say is a lot of our team is just actively working with new customers here. So again, each facility that we want to work with has its own specifications, whether it be regulatory, footprint, process emissions, all of operational, all of these different things. And we're a startup. We're still kind of learning the landscape of what these folks need. And so, that's certainly a big effort for us. And we're actively seeking input from or wanting to talk with folks who might want to adopt the solutions here. What are their specific requirements on site, and then designing for that.
Okay. Well, so you mentioned both in terms of your strategic investors on the kind of the mining and metal side. You've also mentioned cement and others. What's the kind of the next big industrial that you want to engage with? What's the sector, and does it present any kind of new challenges for you, or is it more just just scaling out in a different company?
I'll say we have existing, whether it's investors, customers, partners across all these industries that we've mentioned. But one of the things we found is, a cement plant in Southeast Asia looks very different from a cement plant in the US, right? And so that's where, again, kind of that volume of input from different customers and partners is really what we're looking for. We see this ultimately as a universal solution that can drop into all of these. And so right now what we're doing is, again, as we're testing those different inputs at our current facility, doing that design to ensure that it is universal. And to do that, we need to know what's the range of those customer specs and needs.
Okay. Well, I mean, I can't believe how far you've come in really what feels like a very short amount of time. Your brain must work at a crazy speed to be able to bring together so many new disciplines that you had to learn and to move this forward. But it's really exciting. And to go back to some of your key points, I mean, the main things we hear all the time from industrials is, the kind of traditional general CCS can't take my type of CO2. The traditional general type of CCS is nowhere near my facilities. Traditional type requires, a whole load of cost and energy that then kind of makes us question why we're doing it to decarbonize in the first place. And I think it's really interesting that that your technology can kind of cut through that noise and really present something to those, perhaps a number of organizations, bluntly, who may have given up on the idea or maybe about to give up on the idea that this is a possibility for them. So yeah, interesting times, and it'll be fascinating to hear how this third pilot in Brooklyn goes, but also how these next commercial projects really unfold for you. So thank you for coming on this, and we hope to stay in touch and hear more about those projects as they emerge.
Alex, thank you. This has been a blast, and yeah, looking forward to keeping you and the listeners informed on the progress moving forward.
Thank you.
Thank you for listening to this week's episode. We hope you'll follow Decarb Connect on Spotify, Apple Podcasts, YouTube, or wherever you get your podcasts. If you like what you heard today and are interested in hearing more industrial decarbonisation stories, check out our membership network and events at decarbconnect.com. Join our network and we'll connect you to industrial leaders, tech disruptors, investors and collaborators, all dedicated to reducing industrial emissions.